Wow, well, this is such a wonderful crowd today. I'm Mala Murthy. I'm the director of the Princeton Neuroscience Institute, and I want to welcome you all to this momentous event to celebrate John Hopfield, awarded the 2024 Nobel Prize in Physics for his contributions to the foundations of artificial intelligence. Maybe we can start with a round of applause. All right, so you will hear more about the impact of John's work today from many colleagues at Princeton and, of course, from John himself. I'd like to just kick things off by offering a quote from John Hopfield. When asked very recently about the work he did on recurrent neural networks to earn him the Nobel Prize, he said, "The science which advances technology is the science that gets done for curiosity's sake much earlier." And I really hope that every young scientist was listening to that. John's curiosity led him to major breakthroughs upon which technology that has revolutionized the world has been built. But his motivation was to find a hard scientific problem and uncover its solution. And so, John, we're all so pleased to be here today to celebrate with you and to honor your curious mind. I'd like to begin by introducing the president of Princeton University, Chris Eisgruber.
Thank you, and it's such a pleasure to be here and to have this opportunity to celebrate together with you and our extraordinary Nobel laureate, John Hopfield. I've already had a chance, John, to say a few words at the press conference earlier and to congratulate you, and I know that I'm going to be followed by people who know you and know the field much better than I do. So I'm going to be very brief, but I did want to say a few remarks. I was so struck during the press conference we had and the reception that took place afterwards at what you had done to build the field of neuroscience, both generally and here at Princeton, in ways that were both conceptual and human. Conceptual because of the foundational ideas for which you are being honored with this year's Nobel Prize in Physics, and human in the sense of, I would say, maybe the large crowd that is gathered here, but certainly an extraordinary set of people whom you have taught and mentored and attracted to Princeton University, and who in turn have attracted and mentored large numbers of people. So I'm very grateful to you for that. And I wanted to say congratulations again, and then just a series of thank yous to you. Thank you for the extraordinary work that you have done. Thank you for giving us this special occasion to celebrate curiosity-driven research, as Mala said a few moments ago, to celebrate path-breaking scientific discovery, and to celebrate the community of neuroscientists, physicists, molecular biologists, and chemists at Princeton. It's a very special moment for all of us here. Thank you for making it possible, and congratulations.
All right, thank you, Chris. I'd now like to introduce Jean Schwartzbauer, Vice Chair of Molecular Biology.
Thank you, Mala. What a special occasion this is. Congratulations, John, on this well-deserved honor. My colleagues and I in molecular biology are thrilled that you have received this honor, and we wish you well in going forward with this. I'm speaking on behalf of our chair, Bonnie Bassler, who's out of town. She so regrets not being here, being able to celebrate with you, but she had written a piece of tribute when the news broke and asked me to read it today. Bonnie wrote, "We are all delighted for John for this remarkable recognition of his groundbreaking work. John's discoveries show how research at the interface of disciplinary sciences can transform our understanding of nature and deliver practical applications that benefit society. John combined physics, biology, and neuroscience approaches to probe the brain, developing neural networks to explain how the brain recalls memories. Those discoveries led to the creation of artificial neural networks that are now routinely used by machines like smartphones and self-driving cars. The Nobel recognition is truly deserved, as John's contributions have fundamentally changed the world." But in addition to Bonnie's comments, I'd like to add some of my own comments, having been here when we recruited John to come to molecular biology. And he made significant contributions to the Department of Molecular Biology. So back in the mid-1990s, before many of the people in the audience were born, as I can see, We had a pretty good molecular biology department, but we were sorely lacking in one area, and that area was neurobiology. And so we decided that we really had to build in that area. And normally the way molecular biology builds a new program is to hire talented junior faculty members and let them thrive in our department and grow and become world-renowned. But luckily for us, our then chair, Tom Schenk, learned that John was interested in moving back to the area. And so he brought this idea to the faculty, and we thought, what better way to initiate neurobiology than to have a world-renowned neuroscientist come and join us as the first member of our neuro team. And so I remember the faculty meeting where we discussed this. Tom presented the idea, and we enthusiastically and unanimously agreed that this was a fantastic idea, and obviously we were successful in bringing John to Princeton again. So thank you, John, for coming. Because once you were here, you were really instrumental in building the program, recruiting David Tank, who was delighted to come, I think, because John was here. But also, we were able to assemble an amazing cohort of then junior faculty, like Carlos and Sam and others, who took us from having a simple idea of building neurobiology to actually having a thriving, flourishing neuro group. So that was fantastic. And then in short order, P&I was established, grounded on John's interdisciplinary approaches to advancing our understanding of neuroscience by combining biology, physics, and technology development. And so thank you, John, for your contributions to molecular biology and also to Princeton more broadly, and our heartfelt congratulations on winning the Nobel Prize. Next will be Jim Olson from physics.
Thank you, and congratulations, John. I also want to thank Mala for setting up this big tent. Having not only one, not two, but three academic communities come together to celebrate this well-deserved honor underscores John's broad impact on science and Princeton. And I am honored here to speak on behalf of Bill Bialik, my colleague in physics and the Lewis Sigler Institute, who couldn't be here, sends his apologies, but has shared some reflections of John that I am honored to share with you. Bill writes, of the many things that said in the celebrations on Tuesday, you may remember that a reporter asked, some people are wondering how the work awarded today, which has revolutionized computer science, fits within the field of physics. What would you say to them? More bluntly, she might have asked, but is it physics? This is a question John surely heard many times, even, I gather, long ago here in Princeton. It is a question that many of us who followed him also heard, sometimes in harsh tones. One hopes the Nobel Prize will settle this score, but it's a tough crowd. It was a pleasure to hear John articulate, as he has so many times, in his definition of physics. And I will quote from John now. What is physics? To me, growing up with a father and mother, both of whom were physicists, physics was not subject matter. The atom, the troposphere, the nucleus, a piece of glass, the washing machine, my bicycle, the phonograph, a magnet, these were all incidentally subject matter. Physics was a point of view that the world around us is, with effort, ingenuity, and adequate resources, understandable in a predictive and reasonably quantitative fashion. Being a physicist is a dedication to a quest for this kind of understanding. This evocative vision shines through John's papers, which now span 8 decades, from the 1950s to the 2020s. Parenthetically, Bill notes, it takes great timing to publish in 8 decades when you are only slightly above 90. There is a remarkable coherence to his intellectual style across such a wide range of problems. I don't think he ever did a hard calculation when a simple one was enough. He could engage deeply with experimental details, as with kinetic proofreading, or he could abstract from those details, as with neural networks. I always have been in awe of his touch, knowing how to strike the balance among these conflicting impulses. Only someone with intimate knowledge of the facts could choose so well which ones to use in guiding his thinking and which to set aside. The wisdom of his choices is borne out by what has happened since. John's ideas are more relevant to interpreting today's experiments than those that were being done at the time of his original work. John also once cautioned me about the problems of raising money to do theory. He explained that there are 2 kinds of problems. There are the ones he knows how to do, and therefore are not interesting. And there are the ones he doesn't know how to do. And exactly how do you convince people to give you money to work on something you don't know how to do? I first met John when I was a student, and he came to Berkeley to give a seminar about the energy relay version of kinetic proofreading. He dipped into Baroque details of DNA replication, and he explained how his ideas were analogous to the Overhauser effect in homage to his PhD advisor. He also never made eye contact with the audience until someone asked a question. At that point, John stared intently at the questioner. It was terrifying. I feel fortunate over the years, Bill says, that the terrifying figure I encountered as a student became a mentor, a colleague, and a friend. As a young theoretical physicist interested in the phenomena of life, it was actually hard to find problems where John had not already done something decisive. John once said that his PhD advisor had given him great freedom and that he had tried to do the same for his own students. Perhaps Carlos will say something that helps decode this, but I can say that drawing inspiration from a greater distance was wonderful. John also became a source of wise counsel at essentially every decision point in my career. I remember our long walk together in Aspen in the summer when I was deciding to leave the Berkeley faculty, and as David Tank mentioned, the decision to come to Princeton. John had a moment where his own career trajectory was uncertain. It was both sobering and touching that he was willing to share some of these tribulations. In the end, the solution was to return to Princeton, but as professor of molecular biology rather than as physics. These are the things we do for love. Perhaps this is a good moment to thank Mary for bringing John back to the East Coast. We all thank you. Fortunately for many of us, John's influence in the physics department was not reduced by his masquerading as a biologist. We often say that teaching can be a stimulus to research, and it is wonderful that one of John's most impactful papers on the interplay of quantum and classical dynamics and electron transfer began as a search for an example while teaching. Can you imagine a homework problem that led to a seminal paper in physics? When I was moving to Princeton, he explained that he had reached the stage where he enjoyed being around students, but they didn't need to be his students. True to his word, his door was always open, and he inspired yet another generation. In closing, Bill says, John sets a challenging example, always pushing, as he said on Tuesday, to the fringes of a field, even when the center would be more comfortable. His success in doing this provides a lesson that goes far beyond any particular result. Pushing to the fringes is not a recipe for making friends or for instant recognition. Indeed, even the Nobel Committee needed nearly 2 decades to appreciate fully what John had done. It is wonderful that we can celebrate this moment in Princeton, where his forays into the physics of life began almost precisely 50 years ago. Thank you, John, for bringing us along with you on these marvelous adventures. Thank you. Next up from the Neuroscience Institute, Carlos. Oh, sorry, David Tank from Neuroscience.
Thank you. It is to me a great honor to be given the opportunity to speak at this Nobel Prize celebration with the prize awarded to my longtime mentor, colleague, and friend, John Hopfield. As you just heard in the very moving tribute from Bill, John has had an enormous impact in physics and neuroscience. This impact is the result of his amazing ability to first identify an important problem and then think about it in an entirely new way, creating a new conceptual framework that changes the way people think about the problem. And because of that, what they subsequently work on. I was lucky to be one of the many individuals whose research career was quite literally completely changed when I met him. For me, it was the early 80s, a few months after John's groundbreaking paper on associative memory neural networks came out. Of course, we know it now as the Hopfield network, Hopfield model, and it's the primary work that was cited in the Nobel Prize. The setting was Bell Labs, that's about an hour's drive north of here, where I had gone shortly after getting my PhD in biological physics. In addition to his faculty position at Caltech, John was an MTS at Bell. MTS stands for Member of Technical Staff. It's not a very glamorous title, but it's sort of like a principal investigator. Research groups at Bell were very small. You were lucky if it was more than just yourself. This fostered an incredible degree of collaboration and interaction, difficult, especially at that time, to reproduce in academia. We started working together on extending the Hopfield network, model in new directions into what have become known more generally now as attractor neural networks. There are many ideas and conceptual advances in the original Hopfield model work, that paper, that influenced me personally at that time, and I would argue the entire field of neuroscience more generally. Now, what follows is primarily aimed at the junior neuroscience community here in the audience, who might like to hear a bit more about how that work was a foundation for our contemporary thinking about how brain circuits operate and how we study them. First, the Hopfield network demonstrated what Phil Anderson called, and John mentioned, more is different. In other words, there is more to the network than evident in the properties of its individual parts, the neurons and synapses. There can be, in principle, a collective form of dynamics in the neural activity that is the result of the interactions between these neurons. Those interactions being determined by the specific pattern of connections. This is the idea of an emergent property. Second, that 1992 paper and subsequent work in 1984 was for me, and I think for many, the very first clear elucidation of the idea that it was important and appropriate to think of the activity of the network of neurons as a point in a state space where each axis represents the activity of a neuron. The neural state space is what we call it now. The dynamics of the circuit, in other words, how the pattern evolved with time, could be thought of as a trajectory or flow in that state space. Importantly, John showed mathematically that in this associative memory model, the flow in this state space corresponded to going downhill on an energy landscape. And furthermore, he emphasized that the process of following that trajectory was, in fact, the computation of recalling a memory or pattern from partial information. So this idea of computation as the flow through state space of a dynamical system is really front and center in systems neuroscience now, 40 years later. In the last few years, it has been popularized through the term computation through dynamics. It really started, at least for me and others who followed John's work, with that Hopfield 1982 paper. It is more general than just associative memory, and John showed that in the 1984 paper and subsequent work. For example, a decision circuit, like those considered in things like two alternative forced choice models, could be implemented as an attractor network. In this case, the computation was a decision, and the flow to the fixed point is the choice made. The popular idea of a winner-take-all circuit, which we all know about, is also at its basis a recurrent attractor neural network in the style inspired by the Hopfield model. Over the subsequent years, I was lucky enough to work with John to explore more elaborate forms of recurrent networks where the structure of the computational problem was mapped onto a network's energy landscape, and the flow through state space produced the answer to the computation. It gradually became very clear, I think both to us, it was always clear to John, and the neural community at large, that the pattern of connections was the essence of the computation. It was the way the system was programmed. This kind of thinking, both in recurrent networks and in feed-forward networks like the multilayer perceptron, basically led to the foundation of what we now call connectionism. Our colleague Sebastian Sung has summarized that beautifully, I think, in his book on connectomics. So the notion of collective computation, more is different, in a network of connected neurons, computation through dynamics, and connectionism are very core conceptual ideas in systems neuroscience today that were strongly influenced by the work cited in this prize. Well, were there other implications in the field of neuroscience? Well, the whole conceptual framework he developed implicitly emphasized the importance of recording many neurons at once. After all, the information was in the pattern of activity. You need to sample enough of the activity to understand the population state of the system and follow its evolution in time in order to understand the computation. I can only say that this kind of thinking was not terribly popular in that era 40 years ago when John's paper was published. Even 20 years ago, an eminent prize-winning cortical electrophysiologist said to me, "David, why would we want to record for more than one neuron at a time when we can't even make sense of our single neuron recordings?" No one would say that now. Even that neuroscientist doesn't say that. And thus, in a generation, an entire field changed its way of thinking. In my own career and the group at Bell, starting in the 80s and continuing to this day, it put emphasis on recording the brain in action. At Bell Labs, in what became known as the Biological Computation Research Department, this heralded fMRI, calcium imaging of neural activity, two-photon excitation microscopy in vivo, and even multi-electrode recording tools. Now these neurotechnologies are commonplace in neuroscience labs worldwide, and much of what we do today on a day-to-day basis is an attempt to relate population-level coding and dynamics to computation. I could go on and on about the influence John has had in other areas of neuroscience like olfaction and synchrony. Carlos may discuss this, but I'll just mention one that is important to us at Princeton, continuous attractor networks. The Hopfield model is considered a point attractor, the flow in the neural state space to memory toward a fixed point of the dynamics. Networks with a continuous set of fixed points followed from the work of Chaim Sompolinsky and Sebastian Sun. I should say that John's leadership and impact of the field catalyzed a sizable number of theoretical physicists to move into the field, including Sompolinsky and Sebastian. Sebastian in particular applied it to the model of a circuit in the ocular motor system where the fixed points correspond to gaze fixations. John sponsored that paper for submission. We now know that these continuous attractors are real circuits in the brain. It is, for example, the basis of the ring attractor central complex circuit for heading direction in the fruit fly, a circuit beautifully reconstructed in the recent Flywire Connectome from Mala and Sebastian. Similarly, there is a compelling evidence from another theorist, Ela Fiet, influenced by John, that grid cells in the entorhinal cortex are a continuous attractor network. So in addition to these incredible and conceptual advances, John has been passionate about changing education. In 2002, he participated in the Committee on Undergraduate Biology Education to prepare research scientists for the 21st century. This was sponsored by the National Academy of Science. It was sort of entitled Bio 2010, and it provided a roadmap for modernizing undergraduate biology education. This report and the thinking behind it led to a number of programs in Princeton. First and foremost, it helped David Botstein and Ned Wingreen, among others, garner the resources for what became the integrated science undergraduate curriculum. Second, it catalyzed a group of us to begin a quantitative and computational biology training program at Princeton for graduate students and postdoc. This in turn provided a foundation for the effort John Cohen and I put into the development of the QCN, the Quantitative and Computational Neuroscience Program. And in general, the emphasis and founding of P&I on a philosophy of doing science, heavily weighted to modeling theory and moving more and more from descriptive to quantitative theory-driven experiments using the latest tools in what we now call neurotechnology. So in a very real way, John, you were instrumental in making P&I what it is today. Finally, let me say that John has an office in P&I. You should visit him when he is here. You will learn something new, I promise. John is remarkable in his ability to keep going for years and years. You may not or may not know this, but he has published a number of papers over the last decades. The most recent ones, co-authored with Dmitry Kratov, now at IBM MIT AI Lab, extend that 1982 model in new directions, enormously increasing its memory capacity. As expected from John, this comes with a mathematical understanding so utterly absent in our understanding of other systems in use in neural network-based AI. So in closing, thank you, John, for being such a fabulous mentor and colleague in the early days of my career. You completely changed my trajectory, and more importantly, changed the entire field of neural networks and computational and theoretical neuroscience and biology more broadly. Congratulations on a Nobel Prize, much deserved.
It's an extraordinary pleasure to be here to celebrate John on his Nobel Prize. I'm Carlos Brody. I was John's graduate student and then not his postdoc, and I'll explain what I mean by that in a minute. So I thought that I would speak a little bit about what John is like as a mentor for students and postdocs or not postdocs. I joined his research group at Caltech to do a PhD in computation and neural systems. And that was a PhD program that John had co-founded with a couple of others. I believe that was the first computational neuroscience PhD program in the world. And it was very exciting to join him. What was it like? Well, the tone was set when I arrived on my first day to join his group, and I found that he had left for a year-long sabbatical. And I had, Zoom didn't exist in those days, so I had literally no contact with him at all for a year. I had no idea what a PhD was like, and I assumed that this was normal. And actually, it, in a sense, it was. John has a wonderful essay called Now What that is posted on his webpage, on his P&I webpage, and I absolutely recommend that everybody read it. It's really fun and super interesting to read. And in there, he describes how finding what question to work on is the most critical thing that a scientist can do. And John's thinking was that a PhD is a license to be a scientist, in a sense, and that the most important thing to do was figure out how to find a question. And that the best way to do that was just to try and stumble around and fail and then find another question, and that's how you did it. And so he did not assign projects to his students, and in fact, he didn't write papers with his students then. And other times he has papers with his students, but when I was there, we each wrote our own papers. And so the group was extremely diverse. At that time, there was someone working on using DNA not to encode proteins, but to do computation. There was someone working on speech recognition. There was someone working on computer chess. And I was the one graduate student working on neuroscience. The primary interactions were in the group meetings, which were extremely lively, and there was this very diverse set of things that would get talked about. And what John taught us was to look for and to find the deep intellectual strands that ran under and cut across all those different fields of science, across all of the fields of science. We had very diverse backgrounds. Some of us were not physicists, in fact, perhaps at that time most of us, but that didn't matter. What John taught us, what he led everyone in his group to do, was to the feeling that we were all scientists. We weren't neuroscientists or molecular biologists or physicists. We were scientists. Any paper was fair game. Any topic was something that could be examined and understood quantitatively, and whose deep principles could be compared and often found in entirely different domains. What might outwardly seem like a jumble of different topics was really all one thing: science. It was exciting, it was thrilling, it was empowering, it was very challenging, really not about superficial thinking at all, and it was super fun. As I mentioned, John did not write papers with his students. It was later that I wrote some papers with him, and I'll come to that in a second. John, in addition to all his extremely deep thinking, John has a human side, of course. And while I was in his group, it was that he met Mary, his wife, and fell in love with her, and she moved to California to be with him. But while there, the job opportunities for her there were not that great. And then she got offered the job of being the publisher of Nature here in New York. If you're into scientific publishing, with Mary, who is now an artist, was at the time, I don't know if there's a bigger job than that. And so they decided to move east for Mary. And John was looking for a job east in the New York area and didn't yet have one when he got his group together and told us that he was moving and the group at Caltech would shut down. We looked at him, a little bit surprised, and we asked, so where are you moving to? And John didn't have a place that he was going to at the time. It was a leap of faith. And he leaned back in his chair, and he put his hands behind his head. And with this enormous grin, he said, I'm going to be a kept man for a while. I've seen John extremely intellectually engaged. I've seen him, super focused. Occasionally, when things go really, really well, I've seen him intellectually satisfied. But I don't think I've actually seen him happier than in that moment when all he was thinking of was just being with Mary. It was a wonderful moment that we all remember. So he moved east and eventually to molecular biology at Princeton, as you know, and you've heard about all the wonderful things that have come there. It turned out that at about the same time, I moved to NYU to do a postdoc, and then I started visiting John, and it was then, when I was not his postdoc, that we actually wrote some papers together. As usual with John, the boundaries were not important. What was important was the science. What was important was the questions. The fact that I wasn't his postdoc, who cared about that? And in keeping with this, that the really important things are the science and the questions, John was never one to brag. Back at Caltech, there were some personalities that had the reputation for wanting to win a Nobel Prize, and every year expecting it, and every year not getting it, and the students, we'd make fun of them behind their back. John was not like that at all. He never, ever talked about prizes or anything like that. That was just not something that he focused on. But the students, we pushed him one time, and we flat out asked him, if he thought that he would ever get the Nobel Prize, which, now that I think of it, is kind of a crazy thing to ask. But anyway, we asked it. And what John told us was that he's always had this tremendous intellectual curiosity to open new fields, to go in new directions. And that's what his career has been characterized by. And so that he's founded fields rather than stayed with them for a long time and led them for many years. And that because of that, he thought he would never get a Nobel Prize. And I reckoned that John knew what he was talking about, and I put it out of my mind, and I never thought about it again. And then Tuesday happened. It's an absolutely wonderful thing, and such a delight to see John enjoy this. So well deserved. And please, everyone, join me in a toast to John. To John, congratulations. And our next speaker will be the man himself.
Thank you. Thank you. It's astounding that a group of people like this can bend the truth so elegantly. And there are people I've worked, like David, for all these years. A subject which is ill-defined, but desperately interesting. And you have to just put your backbone into it and give all you can in that direction, or you'll only slide backward. Oh, sit down, for goodness sake. Why am I here? Well, without the Princeton University, without the Neuroscience Institute, and without the Nobel Foundation, I would clearly not be. And I want to thank you to each of these institutions, remarkable in its own age, for nurturing and recognizing my efforts. I have been fortunate to learn from and work with biologists, chemists, electrical engineers, and of course, physicists. Mathematics is essential for it all. I've had exposure both to universities and to places like Battelle, where science is done in a somewhat different fashion. But I'll just remark briefly on the science I've pursued through my career, if I can find any points which haven't already been covered. Princeton saw me as an interesting person to attract from Berkeley as a junior faculty member, and put out the bait, it would be a better teaching environment for me. And in fact, Princeton has been a great teaching environment for me. It's allowed me to develop courses with a few students in them who are not totally afraid of what might take place, and these few students helped define what the course was. And Princeton even stood by me as I wandered outside of my anticipated fields of research, condensed matter physics, toward biology. And you can see the enormous change which David and I have seen. You look at the biology department in 1980, how many people in it who were teaching in it had majored in physics? Zero, absolutely zero. Negative if you could. And now there's no strong departments that don't have people with that kind of background in science, that kind of ability to face quantitative ideas, and with a pursuit which is no stronger than, but in a somewhat direction from the conventional researchers had been in biology. I think all the things I've worked on have already been talked about by the people here, probably with better knowledge than I now have of what I may have written. But I had started with feeling I wanted to move out of physics, which is interesting, but somehow not quite challenging. This is the kind of physics I had been doing. I wanted to move towards something challenging. And the reason I hadn't gone into biology as younger than that was I didn't understand how to meet this kind of challenge. And as you get older, you begin to say, I ought to understand how research is done in my discipline. And so I worked away at what one might call small problems at the edge, where I could see in the nature of the problem that you could describe the biological situation in physics terms, and you could then make some quantitative statements about the relationship between different experiments. And I worked on a set of smaller problems, electron transfer being one of several. And after a while, I was understanding I'd always been in science since age 4 probably, where I liked to take things apart and understand how they worked. And I was lucky enough to have a mother who had also been educated in physics, and she had an old sewing machine. She said, you can take it apart all you like. There's a screwdriver in it that allows you to tackle anything in the house as long as you put the screwdriver back. And I begin to understand that if you want to do a big problem, you have to identify it and see how your tools are going to fit on it. And in wandering around looking for bigger problems, I talked with a lot of people. And one of the results of this was I wound up in a position where I could go 3 times a year to several day-long meetings on neuroscience, a meeting populated by wonderful biochemists, physiologists, anatomists, and so on. You can name all the subdisciplines of neurobiology, but it wasn't populated by anybody approaching biology from a theoretical point of view or trying to actually understand how computations could be done on this framework of nerve cells. And there was, in trying to bring these things together, there was an obvious field, and there were no practitioners in it, because none of the almost neurobiologists who were participating in this, none of them really wanted to learn mathematics or physics. And they realized that they just stayed within their own discipline. They weren't going to do anything big enough to talk about how the brain computed, or ambitiously, to talk about what is consciousness. So I was alone for a while, and that helped, because it takes a lot of bumbling to actually get anywhere. And after a while in this, I was beginning to find some people who were interested in this point of view as well, And there was a field began growing up in the United States, certainly, and more broadly in the world, in which you tried to describe computation as it might be done on a set of neurons. I think the speakers who have spoken already here today about what I've done have extended that end of things as far as you possibly can. I have been astonished by what trying to bring physics together with ideas which come from spin, from electronic circuits, coming from different corners of physics, through mathematics, and spit out of the other side some behaviors of activities of multiple cells, the Moore's different kind of thing, on which you're going to build how neurobiology computes. Well, what should I say? So much has been described already. Let me just describe one more little thing here. The rest is history, as these notes say. I could say much, much more, but coffee calls. I gotta have a short paragraph first. We again face a problem which recurs from time to time, that of creating a technology which threatens its creators. Now we have AI and neural computing. These together are possible examples of original sin, perhaps a global threat to life. In 1973, I was put on a Princeton University recombinant DNA hazard committee as a representative from physics, which had already faced the linkage between the atomic bomb and cheap electricity. This kind of problem is again with us. I worry. But on this happy day, I shout, thank you for coming, everybody. Let's party.